This lesson deals with colligative properties, which are properties that depend on the concentration of particles in a solution, but not on the kind of particles. The first property that we want to deal with involves the vapor pressure of a solution compared to the vapor pressure of the original solvent. Now, when I think of vapor pressure, I like to think of a bucket filled with liquid and holding my hand over the top. I can imagine that particles that are escaping from the liquid are bumping into my hand, and the more of them that escape the liquid, the higher the pressure will be on my hand. If there are only a few of the liquid particles that are escaping into the gaseous state, then I'll feel a relatively low pressure. Now, of course, in reality, you can't do this because our hands aren't sensitive enough. This is simply a tool for the mind to help us get an understanding of what we mean by vapor pressure. So, vapor pressure is a measure of the tendency for a liquid or any substance to turn into a gas. Let's look at what I've labeled here as statement A, which is actually two statements in one. You read it first with the blue words inserted, skipping the green, and then you read it again, skipping the blue words and reading the green, which gives you two statements in one. So let's see what we have here. Adding a volatile solute to a solvent increases the solution's vapor pressure. On the right here, let's say this is a bucket full of water, and it's got a certain vapor pressure. If I add a volatile solute to it, something that evaporates very readily, like acetone or isopropyl alcohol, what will happen is the measured vapor pressure, the pressure that in theory I could feel with my hand, will increase. That's what this statement says. If you add a volatile solute, the vapor pressure will increase. On the other hand, let's go back to what we had at the beginning, assuming that we just have, say, water in the bucket. Now we're going to read the sentence again, skipping the blue words and reading the green. Adding a non-volatile solute to a solvent decreases the solution's vapor pressure. So if I add some non-volatile solute, such as sugar or sand or salt, then the vapor pressure that I'm going to measure will decrease. It will be less than the vapor pressure of the original solvent. This is expressed in an equation form, which we call Raoult's law. And here's what it says. The vapor pressure above a solution at a particular temperature, in other words, the temperature in question, that's what this stands for, at a particular temperature, is equal to the mole fraction of one component of the mixture times the vapor pressure of that component at the temperature in question, plus the mole fraction of another component of the mixture times its vapor pressure at the temperature in question, and so on for every component of the mixture. Ideal solutions obey Raoult's law. Such solutions have a low concentration, that is, they're relatively dilute, and they have solute and solvent particles that are similar in size and have similar intermolecular forces. That's what that stands for. Kind of like there are ideal husbands and there are real husbands, there are ideal solutions and there are real solutions. For the purposes that we have here, we're going to assume that all of our solutions are ideal solutions. So let's do an example problem. A solution of sodium chloride and water has a vapor pressure of 0.854 atmospheres at 100 degrees Celsius. Find the mole fraction of sodium ion in solution. Here's Raoult's law, and the key to this is that the vapor pressure of water at 100 degrees should be recognizable. Hopefully you've been exposed to the idea that at 100 degrees Celsius, the vapor pressure of water is equal to 1 atmosphere of pressure. And for that reason, we can rewrite Raoult's law, putting some of the quantities in that we know. The solution's vapor pressure is 0.854. Here we have the mole fraction of water times the vapor pressure of water at this particular temperature, plus the mole fraction of sodium ion times the vapor pressure of sodium ion at 100 degrees, plus the mole fraction of chloride ion times the vapor pressure of chloride ion at 100 degrees. Well, if you've ever heated up salt to 100 degrees, you know that it has no vapor pressure. Imagine a bucket of salt at 100 degrees and you hold your hand over the top. You will feel nothing. Therefore, the two vapor pressures are both zero, which simplifies this equation to 0.854 is equal to the mole fraction of water times 1 atmosphere. Well, that's very easily solved. The mole fraction of water is then 0.854. In other words, the mole fractions of everything else add up to be 0.146. Since the only other two things in there are sodium ion and chloride ion, and they exist in a 1-to-1 ratio, then the mole fraction of sodium ion must be exactly half of 0.146, which is 0.073.